The goal of this half-an-hour segment is twofold. One, to show you why you're doing these labs, what are the requirements that are being satisfied, and two, to show you practically how to fit this into an already busy, packed clinical schedule and a whole bunch of regulatory requirements that you need to meet. These NRC80 labs, they satisfy requirements from 3 organizations that oversee your education: the American Board of Radiology, the ACGME, and the Nuclear Regulatory Commission, the NRC. The labs also provide you concrete documentation for audits. Any of these 3 agencies can audit you, and so when you want to answer that audit as a residency program or as a resident, then you want that to be easy. You want them to hand them a PDF and say, look, I completed the requirements. And then finally, there's a requirement for having both didactic, which is just someone speaking to you, and hands-on components to your education, and that's what this also satisfies. The specific requirements that relate to radiopharmacy and radiation safety have not changed for probably decades at this point. The requirement that's easy to meet is the 700 hours of training in nuclear imaging. This is something you get when you go on rotation for several months. You'll accumulate your 700 hours. The part that people sweat about more is the 80 hours of radiopharmacy and radiation safety training. And this is the component that's distinct from just coming on to service, that involves actually being taught specific topics that the Nuclear Regulatory Council has outlined and that the ABR and the ACGME essentially have adopted. The ABR just this past March added a more explicit component that they wanted an additional 80 hours of training in I-131 oral administration. This is actually not required by the Nuclear Regulatory Commission, so I wonder if someone copy-pasted the 80-hour requirement from this section here into this other section here. It's certainly a large burden to speak for 80 hours about I-131 administration. So this is just something that the ABR has added just in March that's not represented in the NRC requirements. Finally, you guys all know you have to go hunting for I-131 cases, including 3 cases that are less than 33 millicuries and 3 that are greater than 33 millicuries, and keep a case log, sign it, and then you'll be submitting that to the ABR. The other piece of paper that your program director signs individually for each one of you before you graduate is an attestation form that says that you completed the 80-hour requirement in radiopharmacy and radiation safety. It used to be, just before March 1st of 2021, that this attestation was just a few checkboxes. And one of the checkboxes was that the residency director had followed the regulations that the Nuclear Regulatory Commission had outlined. After March 1st of 2021, the ABR decided to come out with a 30-plus point checklist that laid bare individual curriculum components. And this is really what's led to a lot more attention on how residency programs are delivering this curriculum. What do these labs actually entail? So here we're trying to be practical about your training, but also satisfy regulatory requirements. And the way that each lab is structured is there's a online pre-lab component that you're going to complete. The most important thing here is to review the laboratory worksheet. We'll be revising the online labs a little bit more to make that worksheet more salient to help you find that more easily. But make sure you download this worksheet. It's a Microsoft Word document, and this is very similar to what you did in organic chemistry lab in undergraduate. You have a collection of materials that you need to make sure you have, and we'll work with your NRC director to make sure you have those materials, that you're not scrambling each time to get those materials. And review what you need to do when in the hospital, because we don't want you to take a lot of time away from service to collect data. We also have video demos of me in the hot lab doing a lot of the routine things that you need to learn about, so you can actually just see me talking you through the best practices for things like checking in a package without having to bother the technologist, or depending on the vagaries of who you get that day or how busy the shift is, you'll be able to see a very standard description with best practices of how to do these things. And then there are some multiple choice questions, certainly far fewer than Core Physics Online or Core Physics Live have, but they're targeted questions to make sure that you're alert and oriented to the activity before you start, And then in the post-lab, there are some post-labs that have multiple choice questions as well. That's an opportunity for you to make sure you understand the material that's practical and relevant to the lab. Expect that you're going to take between 2 and 4 hours to complete the experiment. You can do this more efficiently if you have guidance. Let's say a single technologist owns the process of running the experiment with whoever is on for that day. They could accelerate the process for you. But some of this is discovery. It's a little bit of the struggle of uncertainty to understand how you do what you're supposed to do, how to collect the data, and then how to interpret it. That struggle is a productive struggle because it allows you to continue to think critically. When you go on into practice, you're going to have to think critically about purchasing decisions, for example, for software or hardware or business decisions, and or incorporating new best practices and thinking critically about them. So you'll run your experiment in the hospital for 2 to 4 hours, and then you're done with the hospital. You won't be occupying hot lab time. You won't be binding up the service for 4 hours. Really, this is a liberal estimate, and you don't have to be sitting in the hot lab where no one else gets to work in it. There's nothing like that of the sort happening with these experiments. And then finally, you'll have your data collected, and you'll use Google Sheets preferably, or Microsoft Excel to plot graphs to make sense of them, and hopefully uncover things that are not obvious. For example, we'll have you collect data that relates to the 1/r² rule for exposure. The notion that you're taught that exposure decreases as 1/r² relative to the distance from a source, but you'll actually measure with the instruments that you have in the hot lab, the Geiger-Müller counter, the ionization chamber survey meter, and you'll see not only does the 1/r² not perfectly fit the data, there's violations of that in the data that you collect, but then also these two instruments have discrepancies from each other, even though they're being expressed in the same units of exposure. So that's just a preview of the first lab. This is a QR code that takes you to your login page, and I'm going to show you that in just a second. How do the labs map onto the requirements? This is more for our nukes attending who's with us today. You can see that there are a host of detailed requirements from the NRC regulations. These are now recapitulated in the ABR requirements, and each lab specifically has curriculum components that map on. So for instance, in Lab 4, I do a dedicated collection of lectures diving deep into radiation biology, actually more than we cover in Core Physics Online or Core Physics Live. So each of these detailed curriculum components map onto specific NRC80 labs. This goes back to the notion of being auditable for the specific purpose of the NRC requirements. And then how many hours do you get? For each lab, you get 15 hours. We also designate 15 hours for Core Physics Online, which you'll be doing throughout the year. And then finally, Core Physics Live, we have 5 dedicated hours really focused on the core exam and scoring points on the core, including the RISE exam questions, dedicated to nuclear medicine, and so we add that into the total 80-hour requirement. Your schedule for the labs, you'll be able to review this video offline, so I'm not going to read the text in this, but you can see that Lab 1 relates to how do you quantify radioactivity. We'll have you inject a Q-tip with 0.5 millicurie of technetium saline and then take measurements of exposure at varying distances to that Q-tip and plot. So you can see this is not an example of like spending 30 hours in the lab collecting data. This is something that literally you could collect the data in the course of 30 minutes. If you had done this before, you could do it in 5 minutes, but you're probably going to take about an hour between setup and collecting data. There's so much to learn in this simple act. For instance, how you draw technetium saline from a vial is very different from how you draw lidocaine from a vial. You're not going to apply positive pressure to get that liquid to come into your syringe. That's the beginning of your learning. And so just be present and attentive as you go through these labs. And even the seemingly simplest lab is not a matter of checking off boxes, 1/r². Think about the opportunity to draw, learn how to draw, how to do shielding in an actual real situation. The alternative is a 7 a.m. lecture where someone tells you this is what a lead pig looks like and stuff like that. Many of you are going into interventional radiology. Some of you are going to be administering radioactive substances to your patients. And so drawing radiopharmaceutical is a relevant skill. In Lab 2, we'll show you how to be safe in handling radioisotopes. You'll get to practice this syringe technique using methylene blue just to see if you're spilling anything. We'll practice actually spill management. So instead of seeing a PowerPoint like you'll see in Core Physics Live, I'll go with you through, what could they ask you on the core exam about managing spills of different sizes. But here you're actually going to simulate a spill. You're actually going to spill technetium 99M and you're going to clean it up. And so you'll have a visceral understanding of these things that otherwise many residents are memorizing and doing word salad for by the time they get to the core. A really cool element of Lab 2 is you'll see me milk the generator if you don't have access to a generator in-house. You'll see me do that on video, but you'll get to actually understand how do you predict the yield of technetium on Tuesday or Wednesday if you knew what the yield was on Monday. It's kind of magic, but it's also really practical and relevant, and it shows you really need to schedule your patients ahead of time. For a given day, you can support maybe 8 patients in a day. If 2 patients don't show up, whatever amount that you designated for them kind of goes to waste. And if you have 10 additional patients show up, you're not going to be able to support them. So you'll have a much better visceral understanding of how behind the scenes people are actually thinking very thoughtfully about how much radioisotope they have relative to the people that are showing up on the schedule for the day. On Lab 3, you're going to actually prepare your own radiopharmaceutical, and you're going to learn about the chemistry of radiopharmaceutical production. So in a PowerPoint slide, I would tell you that radioisotope connects to a pharmaceutical or biologically active molecule in some way, and that produces a radiopharmaceutical that you can inject. That's nice at the high level, but what you'll get to do here is actually mix your own technetium MDP, which is used in bone scans. You'll be able to do it because it's a room temperature reaction. You'll take an MDP vial and you'll inject technetium saline, you'll mix it, and then you'll do the purity testing that you'd otherwise be memorizing. It sounds complicated, but it's actually routinely done in hot labs, even mini hot labs. And if you don't have the QC equipment to purchase for that, it's actually really inexpensive, and it's available from companies like Biodex. And then I'll show you dedicated lectures. There are dedicated lectures in the online modules that show you the chemistry of how this coordinate covalent bond or chelation is performed, what are the side products, and what looks super simple, which is squirting some liquid into a vial, shaking it, and leaving it at room temperature for a couple of minutes, is actually thoughtful, and there's some chemistry behind it. In Lab 4, by the way, none of this practical experience, I had none of this going through residency. And so, we're in 2021, we should have flying cars by now. At the very least, let's graduate more capable residents when it comes to radiopharmacy and radiation safety. And then in Lab 4, we cover the requirements for radiation biology, but then also, you'll see me in lecture talk about image quality as it relates to gamma cameras, nuclear medicine, nuclear imaging, and that's really practical for the core exam. We want to understand what dials can you turn in a machine in order to improve image quality. That's sort of a recurring theme in the core. The other recurring theme is patient safety. And so in Lab 4, we talk about radiation biology. You'll have better coverage of radiation biology here in Lab 4 than you'll have in Core Physics Online or Core Physics Review, the live review. But then we'll also give you the chance to see for yourself how the image quality in gamma cameras is affected by things like distance to the patient or the different types of collimators that you can use. And you'll be able to quantify spatial resolution and sensitivity. And so this is very simple stuff. You're going to take the Q-tip again, you're going to inject it with technetium 99M saline. You're going to have maybe 3 Q-tips and put them underneath a gamma camera and swap out the collimators and measure distances. And I'll show you how to do that in that lab. But you'll actually be able to convince yourself, oh, when I bring the collimator closer to the patient, I am getting dramatically better resolution as I've quantified here. And so I think by the time you get through labs 1 through 4, which is each of them is 15 hours, but really maybe 1 to 4 hours in the hospital, I think you're going to be so much more knowledgeable and capable at a visceral level by the time you come to the core exam, and certainly if anyone asks you to do anything in practice. So that's the structure. Documentation is obviously at the heart of it for the regulatory administrative part. So you're going to have your NRC director. They need to be involved with this process, the nuclear medicine attending. They're going to sign your worksheet, mainly to make sure that you did something sensible there. Then you'll sign it saying that you finished 15 hours of work on this. You'll upload it to the cloud through our course link, and then if there was any audit, then your course director can just download the full set of worksheets, and this is bulletproof kind of evidence that you put in the 15 hours, and it will be a cut above most programs, although we do have now several programs, probably easily over 100 residents and growing, doing this lab around the country. The last thing I want to show you is just, I want to log in with you to show you the the actual website. So let's see. You're going to go to this website, transcendreview.thinkific.com, and you should have a link from your welcome email. If you don't, you can email support@corephysicsreview.com. You'll log in. There'll be a login button up here. I'm already logged in myself, and then you'll go to My Dashboard, and you'll see your Core Physics Online login, and you'll see your nuclear medicine lab logins. And depending on the program, most programs have now moved to a model where they subscribe to all 4 labs for each of you for the full time that you're in residency, so that you don't have to do a given lab in a specific year. You could even cram in all 4 labs in 1 week. And so you'll click on the labs. Here's lab 1. Let's just click on that, for example. And so here you'll see on the left, you should be able to collapse or expand these chapters. This looks very similar to your Core Physics Online platform. And you'll see it. Here's an overview of the NRC80 Labs. And then what you want to do is look for the materials section, and that's where the worksheet is. So the worksheet is this Microsoft Word document. It lists the materials that you need. You can see the material requirements here is very minimal. You need to get your dose calibrator, your ionization chamber survey meter, and have access to your well counter for a bit. These are all very basic instruments that are in every mini hot lab or macro hot lab. Here we have the worksheet, and the cover page here is where you're going to write your name and sign, and then the supervising attending is going to write their name and sign as well. And then you can see we're basically asking you to fill out a lab worksheet as you go through, as you measure the 0.5 mCi injected into the phantom, inject into the Q-tip. That's where you'll start your learning, just how to draw that technetium saline. And then you're going to measure the Q-tip before and after injection, and then at the completion of the experiment. And you'll find you were trying to measure a 0.5 mCi and inject it, but you're not going to get the 0.5 mCi into the Q-tip. And so hopefully this kind of reasoning in a very abstract situation will help you rationalize about basics of patient care if you're overseeing a hot lab, for example. Here's where you're going to measure at different distances from a source with these other instruments. There's also some mythology that the ionization chamber survey meter, that you're supposed to orient it parallel or perpendicular to the source, and so you're going to just verify that. So you'll see in practice people have superstitions that this is the way we've always done it, and then there's rational, scientifically based practice. And sometimes superstitious practice is actually good because it's grounded in science, we just don't know what the science is. And then other times it's just plain superstition, but you can validate that with many experiments in your practice, sometimes that you need to do that aren't nature and science publications, but that help you guide your practice to be more efficient in terms of time, in terms of money, in terms of decreased adverse events for your patients. And so here's an example of just, let's take this to task and ask whether it matters what the orientation of that instrument is when you're measuring exposure. You'll do data analysis by bringing this data into a Google Sheet. I recommend Google Sheets over Excel. It's easier to work with. And this skill you'll be able to use when you're collecting quality control data for your practice if you're in private practice, or for your clinical research if you're in academics. So learn how to use Google Sheets, how to fit lines, how to plot data, and then you'll paste that data into here, the plots, and then you'll rationalize for me why you see what you saw. And then we're going to take that basic concept, and then we'll have you check in a package, which you can see me do on the video. We'll have you look at I-131 administration and whether it's okay to send a patient out. You'll see me lecture about that in the online modules. I'll give you multiple choice questions so you can understand treatment with I-131. And then hopefully these things will map back on, will connect back to the basic science experiment that you did. So it's no longer just like a rote song and dance, but it actually relates to your basic science knowledge. So that's an example of Lab 1. Labs 2, 3, and 4, they get more and more, they explore different facets as you move forward. And I hope that you can execute on this efficiently in the hospital, and that overall it allows you to think about the nuclear medicine department as a place where magic is happening. Really, what you're talking about here is modern physics being applied to patient care. It's absolutely remarkable that we're using gamma photons and detecting them in detectors, and this is somehow being brought to bear, not in some sort of lab in Switzerland, but it's being brought to bear on patient care every day in the hospital. And so by engaging more viscerally with this material in this setting of of a hospital, hopefully this will give you some more awe and inspiration to be involved with nuclear medicine.
I have a question for you about kind of what your ideal timing would be for these modules. When you developed it, was it more of a kind of one per, one the first year, one the second year, and then two in your third year before core? Or were you thinking more geared towards the residents that are starting to prepare for the exam?
Yeah, thanks for the question. As a practical matter, you have to get this done when you have the chance to get it done. There's nothing more advanced about this material that requires a second or third year resident knowledge in order to do it. So I would dive in and do it when you have a chance, and just start with Lab 1, and you'll get a sense for where you can fit it in. But overall, it would be great if you could finish these labs before you come to the live review. That way, the live review is typically in March, April, and that's where the emotional engagement with the core exam material is at its height, because the exam is imminent. And if you can come to that point, having already done these in a thoughtful way, then the memorization is going to be much easier, and you'll just be more performant and more flexible to questions rather than just trying to regurgitate recalls. If you need to finish a lab in the fourth year, then don't stress about that at all.
How much will I be expected to budget my time for this? Like, how much is going to be me having to help the residents through these experiments?
Yeah, so the model here is, there's some variability in the model on execution of this, but none of it involves one-on-one guidance from attending to resident on an individual basis. The idea actually here is to build efficiency through self-teaching. And so the modules themselves are all things they're going to be reviewing the pre and post lab material independently and conducting the experiment. I think if you have a little sandbox, like a tray with the standard equipment labeled very clearly, this is lab 1, lab 2, lab 3, lab 4, then they're not scrambling around for it. Like a Q-tip box, for instance, so that everyone can just draw their Q-tip when they have it, when they need to do that lab 1. And that's the extent of the equipment, right? There's a Q-tip. They can get their Geiger-Miro counter and the ionization chamber survey meter from the hot lab when it's not being used. So I would say for the nuclear medicine attending, what would be really beneficial that would scale your effort to all the residents is to have very clearly demarcated bins for the equipment, and designate, and then a resident can tell you if they're out of stock of something, and it won't happen frequently. A single Q-tip box will last you for 5 years. And then in terms of guidance, there are two models here. In the first year, you might consider having a group of 4 residents complete a lab together, and doing a direct supervision on the first pass, and with a technologist present, and that way you can kind of delegate to a technologist if there are any questions, specific questions. That would be one option just for the first year. The other option is to just kind of go with the first resident who comes in and see how they do independently, and even allow them to take a role in teaching the other residents how to get through this, just to present briefly in a noon conference for 15 minutes. Here's how I did lab 1, here's the data. And that would actually be very scalable, and it would allow them to express to communicate their scientific results. I think that could be another scalable approach rather than hand-holding one-on-one.
So there will be some supplies that I'll need to make sure we just have on hand, correct?
Yeah, I think mostly these are typically supplies that you would have. The most complicated supply is really just in lab 3, where you have thin layer chromatography, and the equipment is 100% entirely available from Biodex's website. And it's probably like 95% chance that you already have it in the hot lab, because there's like QC requirements, as you know, for these things. Do you mix your own technetium MDP in-house, or do you get that as a unit dose?
We typically get them as unit doses, so that's why I could very easily order the kits and everything and just have stuff on hand for all the residents.
Okay, so maybe you don't do like thin layer chromatography QC for the like technetium HTP. Do you measure how much is unbound technetium before you inject? Probably not, right?
No, that's all taken care of by the outside pharmacy.
Okay.
But I can very easily get the supplies, and we can make sure they have it on hand to be able to do what needs to it.
Awesome. And I think like a single kit goes a long way, and it shouldn't be very expensive. Also, the HTP, the nice thing, it should be fine at room temperature in a single box with a bunch of vials will cover all of your residents for like 4 years, right?
Well, they'll expire eventually, but I suppose an expired one is actually just as good of a teaching method as
oh yeah,
new one.
As good or even better. So because you can see like stuff go even more wrong when it comes to unbound stuff, oxidized materials and stuff like that. So yeah, that should be good. Okay, well, it's any final questions? It's 1:34, and I promised a half an hour. I have nowhere to be, but I really hate taking up people's time on Saturdays, and I appreciate you guys coming out for that.
Thank you for taking the time. We appreciate it.
Yeah. So if you guys have any questions, email me at support@corephysicsreview.com. And if it's just I can't get access to my account or something, then one of our course coordinators will reply to you and help you out with that, usually within 24 hours on a weekday. Or if you email on the weekend, then it might just be me that replies to you, or they'll reply to you on Monday. And if you have any technical questions, you can email that address as well, and I'll answer any technical questions you have. And have a good rest of the day. I'll catch you guys later.
Have a good weekend. Thank you. Bye.
Bye.